calculus students here are the increasing and decreasing functions and the first derivative test, where we're going to figure out how we can figure out with calculus where functions are increasing and decreasing, and also the first derivative test will tell us if we're looking at a maximum or a minimum. First of all, here's a formal definition of increasing and decreasing. I think you get the idea that the function's increasing, that as you go from left to right, the y values go up, and that's what's implied here. It's decreasing as you go from left to right in the x's, that is x1 is less than x2, then the y values will decrease. And so the first y value is bigger than the second y value. And we see that in graphs here. We're decreasing. Now a lot of kids mistakenly think that you're going up on both sides. Well, no, as we go from left to right, just like when you read, this is considered decreasing, constant, increasing, because as you go from left to right. Now, associated with that is a way we can predict if a function is going to increase or decrease by looking at its derivative. And it takes us back to the red part of the red-green show. That is, change in a function leads to sign in the derivative. And now in this chapter, we're going to spend a lot of time looking at the sign of the derivative to predict how the original function is changing. So, that's what's listed here. If the derivative is positive, then f is increasing. Positive on the derivative means the original function is increasing. If the derivative is negative, then the function is decreasing. Negative on the derivative means the original function is decreasing. And if the derivative equals 0, then you're doing neither. And that could mean you're shifting from increasing to decreasing or decreasing to increasing, which means a relative max or min. Or maybe you're just staying constant at a constant level, so the slopes of all the tangent lines are 0. Now, let's look at an example here of finding out the open intervals on which x cubed minus 3x squared is increasing or decreasing by looking at the derivative. And then we can check it by looking at the graph. So let's start by taking the derivative of this function, f prime of x then, equals 3x squared minus 3x. And we look to see what the critical numbers are, that is when this is equal to 0. So 3x squared minus 3x equals 0. Let's factor out a 3x, leave behind x minus 1. So we see at x equals 0 and x equals 1, something's going to happen. And what we can do now is test some points in between here. There's a couple ways to look at this. You can look at this function, this derivative, and look at its graph and say the derivative is 0 at x equals 0 and x equals 1, and it's a happy parabola. So it's going to go like this. So here the derivative is greater than 0 in this interval. It's less than 0. It's greater than 0 in this interval. And in between 0 and 1, the derivative is less than 0. That means that the original function is going to be increasing, then decreasing, then increasing. So we're going to be increasing f is increasing when x is between, it's left of 0, x is less than 0, or when x is greater than 1. F is decreasing when x is between 0 and 1, because that's where the derivative is negative. Now let's circle these ideas and make sure you understand why in each case. F is increasing when x is less than 0 or when x is greater than 0 because that is when the derivative is greater than 0. And f is decreasing between 0 and 1 because that is when the derivative is less than 0. Okay? Now let's see if that bears out in a graph. And sure enough, less than 0 and greater than 1 is when the function's increasing. Between 0 and 1 is when the function's decreasing. And we looked at this before in the red-green show. Remember we talked about look at change. The function's increasing here, so its derivative is positive. And this is a graph of f prime I'm doing down here. Here it's also increasing, so the derivative is positive. Here it's decreasing, so the derivative is negative. And the derivative, remember, was this happy parabola that we have over here. Okay, let's look at some more ideas. This is just a term involving the idea of strictly monotonic means you're always increasing or always decreasing. Some people debate whether this point right here is actually a point of increasing because the derivative is 3x squared and f prime of 0 equals 0. So this is one thing you have to watch out for. We can still consider this increasing because as we go from left to right, the points continue to get higher and higher. Okay? So we call this strictly monotonic function because it's always increasing. Notice if it flattens out in between here, like it's 0 from 0 to 1, now it's constant there, it's no longer increasing. Okay, just a term there for you. Now, here's going to be our guideline for figuring out when a function is increasing or decreasing. If it's a continuous on this interval from a to b, locate all the critical numbers, that is where the derivative is 0 or undefined. Determine the sign of the derivative in between those values, and then figure out if f is increasing or decreasing. Okay, so it's a slightly different technique than what I was showing you here, where I actually graphed the derivative. Because to me, that was an easy way to figure out when is the derivative positive and negative by recognizing a parabola. But sometimes you might not recognize the graph that results. So I'm going to give you both techniques, both book technique and my technique. So, okay, here's an example of x squared minus 6x plus 8. Let's find out when the function's increasing and when it's decreasing. Now we can look at the graph to see that it's going down and then it's coming up. But where does it actually turn around here? So we can look at the derivative. That is f prime of x equals 2x minus 6. Set that equal to 0. It's not going to be undefined anywhere. So x equals 3. And here we can look at each of these intervals separately. Extend the page a little bit here. Here's x, and we're going to look at 3, and we're going to test some points on either side, and here's f prime of x. So right at 3, the derivative is equal to 0. Let's test a point to the left of 3. If I put 2 in, then, and it can be any point to the left of 3, I put 2 in, the derivative is 4 minus 6 is negative 2. And so that means that the original function, f of x, is decreasing. If I try 4, I put 4 into the derivative, I get 8 minus 6 is 2. That's positive, therefore the original function is increasing. So we have it decreasing in the interval to the left of 3 when x is less than 3. You can also say negative infinity up to 3. It's increasing when x is greater than 3. You could also write that as 3 to infinity. Now, this is where we're going to get into the first derivative test. That is, we have a first derivative equal to 0, so we suspect that that's a relative max or min. Now, which one is it? Well, it goes from decreasing to increasing, so it's a relative min. And that, friends, is essentially the essence of the first derivative test. If you've got a critical number and you see a change in the sign of the derivative, now you can predict whether it's going to be a relative max or min. So let's take a look at that back in our other notes. So let's try and fathom the first derivative test here. And it's a way of using the derivative and the sign of the derivative on either side of the critical number to predict if you got a relative max or min. Notice here we can see from the picture they got a relative max at 0, 0 and relative min at 1, negative half. And that when we took the derivative, f prime of x, we got 3x squared minus 3x. And we got our critical numbers when we set that derivative equal to 0. Factor out the 3x, and we get x equals 0 and x equals 1. Well, it's easy to see from the picture which one's a max and which one's a min. But how can we tell from the first derivative test? Well, here it goes. First, we look at our critical numbers, which we talked about before. Those are the things that make the derivative 0 or undefined. And then we see what happens to the sign of the derivative as we go across those values. So in our example here, we look at what happens as x. We have these critical values at 0 and 1. We're going to test some points on either side to see what's going on here. We know the derivative at each of these is 0. But let's try some points on either side of them. Let's try negative 1. So let's do our trial points in blue here. These are our test points. Test something like negative 1 in the derivative, and you get 3 plus 3 is 6. That means the original function, f of x, is increasing. And now let's try a point in between here, like a half. Put a half into here, and we get 3/4 minus 3/2. That's going to be less than 0, so that's going to be negative. So that means the function's decreasing. So if we go from increasing to decreasing, that means we have a relative max there. Now, as we test a point beyond 1, like 2, put 2 into the derivative, and you get 3 times 2 squared, 12 minus 6. 6 means that the function then, since the derivative is positive again, is increasing. So we're going from decreasing to increasing. Decreasing to increasing means you have a relative min. So this is a relative min when x equals 1. And now here's some more general diagrams of what's going on here. At a relative min, you go from decreasing to increasing, so the derivative goes from negative to positive. And a relative max is when the function increases and decreasing, so the derivative is changing from positive to negative. Notice here, we've got a 0 derivative, levels off, but the derivative doesn't change sign, so we don't get a max or a min. And those are the cases defined over here, and that's the first derivative test. Look to see how the derivative is changing as you go across that critical number. Check a point on either side of the critical number. Now notice I was careful here that I didn't go too far away. Like I didn't take any point to the right of 0. I wanted one in between 0 and the next critical number, so that's why I picked a half. Okay. The only places that you can change sign on the derivative is at the critical numbers. So that's why we focus on those. Okay, let's apply the first derivative test to this. Find the relative extreme of the function given by this function. So let's start with the derivative. The derivative is 6x squared minus 6x minus 36. And we set that equal to 0. We don't have anything in the denominator, so we don't have to worry about making it undefined. Let's divide through by 6. That's not going to lose us any roots. And factor down to x minus 3 times x plus 2. So we get our two numbers, critical numbers at x equals 3 and x equals negative 2. Now you want to make a little chart and check what's going on at each of these things. At x of negative 2 and x of 3. Now we already know what happens there in terms of the derivative at those points. The derivative is 0, the critical numbers. We want to try some points in between here. Like 0 is a nice number to try in between negative 2 and 3. And the derivative is 6x squared minus 6x minus 36. When we put 0 into that, we get negative 36. What does that tell us about f then? F must be decreasing. You can use this downward symbol too, like that. I'll understand what you're talking about. Let's try a point to the left of negative 2. Let's try negative 3. Now this gets a little harder to substitute in. Notice we might prefer this format for it. 6 times x minus 3 times x plus 2. And so I get 6 times negative 6 times negative 1, and that's going to be 36. Well, that's going to be increasing then. Since the derivative is positive, we're going to be increasing. So by the first derivative test, at this critical number, the derivative changed sign from positive to negative, so when the original function went from increasing to decreasing, so therefore we have a relative max there. Now finally we put in 4, and we end up with 6 times 1 times 6, or 36. So we're back then to a positive derivative, which means that the function, the original function, is increasing. So if it goes from decreasing to increasing as we cross this critical number 3, we must be at a relative min, because we went from decreasing decreasing to increasing, that means a min. So at negative 2, we can put that into the original function to find out what our value is. We can also see what that here. Let's check this 58 here. How'd they get the 58? They put negative 2 into the original function, and we can do that synthetically. 2, negative 3, negative 36, 14, zip. 2, negative 4, negative 7, 14, negative 12, 24, and there's your 58, and I lost something here because that's a 22. 44, 58. So that's where they got the 58. So there's the relative maximum occurring at negative 2 comma 48. And you can test it also with 3. What happens with 3 when you put 3 into 2? Negative 3, negative 36, 14. Do a little synthetic substitution here. 6, 3, 9, negative 27, negative 81, and sure enough you get negative 67. So that's where they got that. Okay, so that's how we can find our relative extrema on an interval. Okay, now let's apply the first derivative test on this. X squared minus 4 to the 2/3. We look at the derivative, and that's 2/3 x squared minus 4 to the 2/3 minus 1, or negative 1/3, and don't forget the derivative of the inner function, 2x. So we get for a derivative 4x all over 3 times x squared minus 4 to the 1/3. So we have a couple possibilities for critical numbers now. For critical numbers, remember it can be where the derivative equals 0. So in this case, that's where the numerator equals 0. So we set 4x equal to 0. So that's one consideration. We can also get critical numbers when the derivative is undefined, and that would be when the denominator of a fraction equals 0. So we set 3 times x squared minus 4 to the 1/3 equal to 0, and you get x squared minus 4 then basically equals 0. So x squared equals 4, x equals plus or minus 2. So we got 3 critical numbers to look at, and they are at negative 2, 0, and positive 2. Save some space in between each of these because that's the critical thing we want to look at for the first derivative test. How do these change as we go in between those numbers? So here's our values for x. Here's our candidates for relative max and mins, and what's going on with the derivative, and we want to see how that predicts what's going on with the original function. So we got undefined when we looked at the derivative at 2 and negative 2. The derivative is undefined. And at 0, the derivative was 0. Let's find out what's happening in some of these things in between it. Now, it might be a good idea to jot down the original function, x squared minus 4 to the 2/3. Oopsie. Oh dear, where are we here? X squared to the 2/3, and the derivative, because that's what we're going to have to test all the time here, this 4x over 3 times x squared minus 4 to the 1/3. The derivative equals, let's make a little more room here, hang on. I forgot to continue recording here. Okay, I just put in the name for the derivative up here, f prime of x equals 4x over x squared minus 1/3. And I've got the values here for what's going on with the derivative in each case. Negative 2, 0, and 2 are critical numbers. And negative 3, negative 1, 1, and 3, I put them into the derivative function to see what's going on. And I end up with, at negative 3, 4 times negative 3 over negative 3 squared minus 4. Now, I don't have to get the exact answer here, I just have to know the sign of it. And I'm getting a negative number over a positive number, so that's negative. The derivative is negative, means the original function is decreasing. And here, when I put negative 1 in for x, I get negative 4 over a negative number, so that's positive. The derivative is positive, means the original function is increasing. So since we change sign from a negative derivative to a positive derivative. That means the function went from decreasing to increasing, so it goes down and comes up, and that means we have a relative min at x equals -2. And I put -2 back into the original function to see that the y-coordinate is 0 there. Similarly, at 0, we see a change in sign of the derivative from positive to negative, so the function goes from increasing to decreasing, so it must be relative max. And you put 0 into the function, and you get -4 to the 2/3. You can check on your calculator as the cube root of 16. Finally, as we check out the critical number at 2, which made the derivative undefined, the derivative goes from negative to positive, so the original function goes from decreasing to increasing, so your decrease and then increase means you must have a relative min there at 2, 0. And again, we got the 0 from putting the 2 back in the original function. How does this check out with our picture? Great. Notice here we've got some sharp corners because that's where the derivative is undefined. And here we have a 0 slope. Those were our candidates, our critical numbers. And in each case we saw a change in sign in the derivative. Notice the original function isn't changing in sign, it's always positive. But the derivative is changing sign. Now, some technological pitfalls is sometimes some calculators don't handle this 2/3 power very well. And you might have to split it up into squaring it and then raising it to the 1/3 to get that middle section. Because some calculators just don't like the 2/3 power. Our T89 doesn't freak out on that. It does a nice job. Now, remember we kept talking about you have to consider when is the derivative undefined as well. And also, if there's parts of the original function that are undefined, you have to consider those as critical numbers as well, because the function might be changing sign and its derivative might be changing sign there. So let's look at the first derivative test on this. First we start by doing the derivative, and there's many ways to do the derivative here. We could leave it in this form, or actually change it to f of x equals x to the 4th over x squared plus 1 over x squared, and we can avoid having to do that whole quotient rule thing, right, as x squared plus x to the -2. Now the derivative is just 2x plus -2x to the -3. So we have a derivative of 2x minus 2 over x cubed. And we can set that equal to 0 and undefined. Now, setting the derivative equal to 0, we get 2x equals 2 over x cubed, or x to the 4th equals 1, or x equals plus or minus 1. Setting the derivative undefined is going to occur when the denominator, any of the denominators equals 0, and our one denominator is x cubed, so x equals 0 is also a critical number. Notice it's also where the original function is undefined as well, and it's a vertical asymptote in the original function. So we can make our chart again, where we look at values of x, look at values of the derivative, and see how that predicts what's going to happen with the original function. And let me just clean this up a little bit here, because our derivative now, we need to have that formula in here for the derivative, and that was 2x minus 2 over x cubed. 2x minus 2 over x cubed. The original derivative, 2x minus 2 over x cubed. And the original function is x to the 4th plus 1 over x squared. So we have three critical numbers at -1, 0, and 1. And 1 and -1 made the derivative 0, and 0 made the derivative undefined. Now let's test points in between. So we try -2 in the derivative. That's -4 minus 2 over x cubed, so that's minus 2 over -8. That's -4 plus a 4th, that's negative. So that means the function is decreasing. If we try -1/2 between -1 and 0 here, put in -1/2, 2 times -1/2 is -1, minus 2 over -1/2 cubed is -1/8. that's going to be hugely positive. That means the function's increasing. So we went from decreasing to increasing, so it must be a relative min. Now 0 is undefined, so we've got to be careful here. The derivative is undefined, but the original function is as well, so there's no way it could be a relative max or min. So this is a vertical asymptote, so it's not a max or min. Even though the first derivative test might say otherwise, remember it has to be a critical number, so it has to be in the domain of the original function. But we're going to look at this because we're going to see that when we try a half in here, if you put in a half, you get 1 minus 2 over a half cubed. And you get 1 minus 16, you get negative 15. That's negative. Remember, we're focusing on the sign of the derivative. So that means the function's decreasing. See, if we had ignored this, we'd be in trouble because we might have accidentally put in negative a half or even 0 and come up with the wrong idea here. Let's put in 2. We get 4 minus 2 over 2 cubed. That's going to be positive, which means the original function then is increasing. If we go from decreasing to increasing, we must have a relative min. So we have no relative max in this one. We just have relative mins at 0, at negative 1 and 1. And if we put those into the original function, our relative min is at negative 1 comma, what do we get when we put negative 1 up here? You get 1 and 1, you get 2. And when you put 1 in, you also get 2. Relative min's at negative 1, 2, and at 1, 2. And that bears out on our graphs. Notice at x equals 0, there's a vertical asymptote. So we don't get anything in there. Okay. One other thing I want to look at quickly is reviewing the red-green process for graphing our derivatives. And that shows up right here. Now that was determined function increasing, decreasing. It comes up a little later on in the homework here, where they probably have you do some matching. Yeah, look at the figure and draw its derivative. And so in this figure here, we see in 45, the function is decreasing. So that means the derivative will be negative. Then the function's increasing, so the derivative will be positive. And right here we have a relative min. Turns out to be an absolute min as well, so the derivative is 0. Now we're going to review the green part of the show in the next section. But remember they had to do with concavity. This whole thing is concave up, so the derivative will be increasing. And so that's what we end up with for our derivative is a line that goes from negative to 0 to positive, and it's increasing the whole time. So that's how you can sketch a derivative. You can also say, hey, this looks like a happy parabola, and the derivative of the parabola second degree equation is a first degree equation.